The following is an AZPM original production.
Arizona Science is supported by Research Corporation for Science Advancement.
For Arizona Public Media, I'm Tim Swindle, Professor Emeritus of Planetary Science at the University of Arizona, and this is Arizona Science. Joining me today is Dennis Zaritsky, Regents Professor of Astronomy at the University of Arizona. Welcome, Dennis.
Thank you. Thank you for having me.
Dennis, you study all sorts of things involving the structure and evolution of galaxies, but one of the things that fascinates me is that you're studying dark matter. What is dark matter?
Well, we don't know. That's the big mystery, right? So we can infer its presence, but we don't yet know what it is.
Well, how can you infer its presence?
We know how things should move. We have equations that explain how stars, other galaxies should move in the universe, and we observe how they move, and they don't move as what we would expect them to if all that was there was what we see. And therefore, we infer the presence of other matter that we don't see.
And this is matter that has to have an effect of gravity, right? That's
right. What we're measuring as things orbit around is the force of gravity. The problem there is that we have a model for gravity. And so the question is whether our model for gravity is wrong or whether there is this extra mass out there that's the dark matter.
And how is dark matter related to dark energy that we also hear about?
Yeah, another mystery. On the surface, they're not related. So you could have one or the other. In fact, for a long time, we thought we just had dark matter and that the rest of the universe behaved exactly as we expected. Subsequent measures showed that that was wrong too. And so we have this other thing called dark energy, which propels the universe to accelerate its expansion, whereas dark matter is something that acts like extra mass.
There have been a lot of suggestions about what dark matter actually is, but you've spent a lot of time testing various ideas. What are some of the ones you've tested?
Primarily, we've tried to see if this force, if the issue really is that we have the explanation for gravity incorrect or correct. And so what we did was use something called the bullet cluster to test this. So this was a study led by Doug Clow here, who was a postdoc of mine back 20 years ago or so. And again, the problem is that if you don't understand gravity fully, your expectations are incorrect. And therefore, when you observe a discrepancy, you don't really know what the source of that is. In the bullet cluster, what happens is that two clusters run into each other. And that collision...
Two clusters of galaxies.
Two clusters of galaxies. And so what that does is it separates most of the normal matter, which in these clusters is gas, which the gas collides and sticks together. And the dark matter moves through the collision, if there is dark matter. So now you've used this cosmic accelerator to separate the normal and the dark matter. So if you still see dark matter where there now is no normal matter, you have direct evidence for the dark matter. And that's what this bullet cluster allowed us to do. We did see the evidence for the dark matter displaced from the normal matter using a method that looks at the shapes of background galaxies to infer the presence of mass along the line of sight.
So that leaves the question again, what could dark matter be?
So it ranges for anything from primordial black holes, so sort of macroscopic objects, big objects, to subatomic particles, even particles that have such a low mass that they behave like quantum mechanically, like a wave on galactic scales. So there's a full range of masses, and that just shows how ignorant we are. We've been able to eliminate certain regimes in that range. So there are things that we can now rule out, and it's a process of ruling things out. And there are many, many experiments going on, particularly on the particle side, to try to track different candidates. So far, all we have is null detections.
Do you have a particular favorite or one that you're working on now?
I like this very, very lightweight particle. It's referred to as fuzzy dark matter because it has very interesting predictions that we could perhaps test. And basically it is that the dark matter would have these ripple effects in the halo, and perhaps we can actually find those ripples, and they would have an effect through gravity on normal matter.
Well, good luck with chasing dark matter.
Thank you.
This is Tim Swindle, and you have been listening to Arizona Science. Our guest today has been Dennis Zaritsky, an expert on how galaxies evolve. You can hear more of this conversation and others on our Arizona Science podcast at azpm.org.
Thank you to Research Corporation for Science Advancement for their support of Arizona Science. AZPM podcasts are made possible in part by donations from listeners like you. Learn more at support.azpm.org. Thank you.